Good morning. We find the time complexity of several common algorithms in this lecture, including finding the maximum element of a finite sequence, the linear search algorithm, the binary search algorithm, and the bubble sort algorithm, and the insertion sort algorithm. Algorithm run. 1. Finding the maximum element of the finite sequence. The first thing we do is we write some C++ code that finds the maximum element in a finite sequence. And we compute the cost. So what I'm going to do is I'm going to start out by assigning the maximum element the minimum value. And then I'm going to index through a list of values that are given in array A, and looks like I need to give that their integer values, and I'm going to find out if the maximum value by sequentially comparing them to the most recently found maximum value. So I figure out what the cost of this, and it turns out to be T of n turns out to be 4n plus 3, and we guess that that this algorithm has linear time complexity, and we demonstrate that by finding f of n is equal to n, and c is equal to 5, and find an n sub naught, and then we can say T of n is O of n, or linear time complexity, because we have found witnesses c equal 5 and n sub naught equal 3 that make the magnitude of T of n sub naught less than or equal to the c times the magnitude of f of n sub naught for n greater than or equal to n sub naught. Our next algorithm is a linear search algorithm. It has the same time complexity as our find the maximum element. We're just looking for a key, and in the worst case, what could happen to us is we could match our key as the last thing that we compared. So we have much the same analysis here, and we find that T of n is T of n sub naught is less than or equal to, or T of n is less than or equal to C f of n for n greater than n sub naught. Algorithm 3, the binary search algorithm. What we do here is we set limits, low being the low bound and high being the high bound. We assume that the elements of array A are sorted in ascending order. We guess the middle, and if the middle is the value that we're searching for, then we return that value. If not, we decide if it's in the top half, and if it is in the top half, then we eliminate the bottom half from the search. If it's in the bottom half, we eliminate the top half, and we continue to refine, throwing away half the remaining values to be searched until we have only one remaining value in the first case. Insofar as we throw away half the remaining values, this becomes a logarithmic function, and because we're dividing by 2 each time, and we come out with the time complexity of T of n is 8 times the ceiling of log 2n plus 3, and we eventually find that this function is O of log 2n, because we found witnesses Cn and n sub naught equal 8 that satisfy the definition for big O. For bubble sort, what we're doing here is we're indexing through our unsorted list, and whenever we find an element that is less than its neighbor with a smaller index, what we do is we move it, we exchange it, and we keep, this works much like bubbles underwater, that they have a tendency to move towards the top, where the top is the top of the list. And eventually we find the list is sorted. And to do this, we find a T of n that's n squared, which we know to be true because if you have the smallest item there, it may take 2 passes through the list to acquire it. So, and each pass has n iterations. And so we find that this is O of n squared, the bubble sort, another sort that we should never use again because it has poor performing characteristics, and we can find sorts that have O of n log n, n log 2n tail, and those are the sorts that we should use. An insertion sort is another sort that has poor performance characteristics. We insert elements in their proper order, and we eventually find that T of n is 5n squared minus 11n minus 12, and we find that T of n is O of n squared, and same as the bubble sort. And that concludes our lecture.